Welcome to the 7th video in the Essential Extract Vector Calculus series. In this video, we're going to talk about Green's and Stokes's theorems. Green's and Stokes's theorems are two-dimensional generalizations of the fundamental theorem of calculus. We'll talk about several different forms of Green's theorem, which you might see, and we'll also talk about several applications of these theorems, including applications to Maxwell's equations in physics. If you're following along with the Summary of Vector Calculus handout, we're now almost at the bottom at these two equations here. A link to the handout can be found in the video description below. Before we look at the statement of Green's theorem, as a point of reference, I'd like to remind you of the statement of the fundamental theorem of calculus. The fundamental theorem of calculus says that the integral from a to b of f prime of x dx is equal to f of b minus f of a. I've written it from right to left here for comparison with the theorems that we're going to see later in this video. There are three things which I'd like you to notice about this formula. The first is that the object on the right-hand side is a one-dimensional integral. In other words, it's an integral over an interval from a to b. Second, the object on the left-hand side is a zero-dimensional integral, or a sum, over the boundary of the interval. You can think about the minus sign here as indicating an orientation of the boundary. The third thing is that the object that I'm integrating on the right-hand side involves the derivative of the object that I'm integrating on the left-hand side. These three features of the fundamental theorem of calculus form a pattern that you can see repeated in Green's theorem and Stokes's theorem and in the divergence theorem in the next video. One of the main differences is that in Green's and Stokes's theorem, the integrals involved are two- and one-dimensional, while in the divergence theorem, they're three- and two-dimensional. There are also some other differences with what exactly the integrands look like, but we'll see those when we get to the precise statements of the theorems. Now let's try to understand the statement of Green's theorem. Green's theorem says that for a region D in the plane and functions p and q from R2 to R, the oriented integral over the boundary of D of p dx plus q dy is equal to the double integral over D of the partial of q with respect to x minus the partial of p with respect to y. This may seem like a lot to digest when you first look at it, so it's helpful to see how it fits the pattern that we just described. First of all, the object on the right-hand side is a two-dimensional integral over a region D in the plane. Second, the object on the left-hand side is a one-dimensional integral over the boundary of the region. The circle on the integral on the left indicates that we're taking the boundary with the positive orientation. If you want to remind yourself what the positive orientation is, you can see video number 3 in this series. It's also worth mentioning that the one-dimensional integrals on the left-hand side are line integrals of the second kind. As a matter of notation, when we write the integral of p dx plus q dy, we really mean the sum of the two line integrals, integral of p dx plus integral of q dy. Most people prefer to write that this way, though, for aesthetic and typographical reasons. The third thing that you should notice about this formula is that the integrand on the right-hand side involves the derivatives of the integrand on the left-hand side. Of course, there are some assumptions that need to be made in order for this formula to hold, and we're glossing over that. But in practice, we are going to want to assume things like that the boundary is a finite union of piecewise smooth, simple closed curves, and that p and q have continuous first partial derivatives in an open region which contains D and its boundary. There are a lot of different applications of Green's theorem, and just to mention a couple, if it turns out that the integrand on the right-hand side is relatively simple, then Green's theorem gives an easy way to compute the line integral on the left-hand side. An example where you can see an application like this is in the proof of the Cauchy-Goursat theorem from complex analysis. If you want to see the details of how this works, you can check out video number 4 of the Essential Extract Complex Analysis series. I'll put a link to that video above. A second way that Green's theorem is sometimes applied is to compute double integrals over certain regions D by choosing p and q appropriately and then computing the line integrals on the left-hand side. There are a number of interesting applications like this, but just to give you the flavor of what I mean, let's suppose that you just want to compute the area of some region in the plane. Well, then you can make any choice of p and q with the property that qx minus py is equal to 1. As long as you can compute the line integrals on the left-hand side, what you get is going to be equal to the area of the region that you're interested in. One possibility is to take p equal to 0 and q equal to x, but there are other possibilities as well. This leads to some interesting mathematical formulas, and it also has some applications to engineering. Before moving on to the statement of Stokes's theorem, let's talk about a second and third form of Green's theorem which you might encounter. The second form of Green's theorem is what I would call a vector form of Green's theorem. Here, let's suppose that we have a vector field f defined on some region D in R2, and let's suppose that the component functions of our vector field are p and q. Consider the line integral of the third kind, integral around the boundary of D of f dot dr. You might remember that this line integral is equal to the integral around the boundary of D of p dx plus q dy. If you didn't know this, or if you can't remember why this is true, you can see the derivation in video number 4. Just fast forward to the 720 mark in that video. Combining this observation with the statement of Green's theorem immediately gives the formula that the integral around the boundary of d of f dot dr is equal to the double integral over d of qx minus py. This is an important form of Green's theorem, and as you'll see later in this video, it paves the way for the generalization to Stokes' theorem. The third form of Green's theorem is what I would call a divergence form of Green's theorem, and it takes a little bit of setup to state it. Just as in the second form of Green's theorem, let's suppose that f is a vector field from R2 or from some subregion D of R2 to V2. The component functions of f again are p and q, and this time let's parameterize the boundary of D with the positive orientation by a vector function R of t whose component functions are x of t and y of t with t running from A to B. In order to state the third form of Green's theorem, I want to define a unit normal to the curved boundary of D. Remember that the vector function t of t, defined by x prime y prime divided by length of r prime, gives a unit tangent to this curve at every point. It's not difficult to see that the vector function y prime comma minus x prime divided by length of r prime is perpendicular to the unit tangent and also has length 1. Therefore, this defines a unit normal vector to the curve at every point. Now let's consider what we get when we integrate f dot n ds around the oriented boundary of D. Notice that this is a line integral of the first kind. Using our parametrization and the definition of line integrals of the first kind, this is the integral from a to b of the quantity that you see here. When we multiply the length of r prime of t through, this simplifies, and you might recognize that it's now a sum of two line integrals of the second kind. Now, applying Green's theorem to this quantity, with minus q playing the role of p in the original statement of the theorem and p playing the role of q in the original statement of the theorem, we find that it's equal to the double integral over d of px plus qy. You might recognize that this is precisely the divergence of the vector field. That's the reason why I called this the divergence form of Green's theorem. It says that the integral over the oriented boundary of D of f dot n ds is equal to the double integral over D of the divergence of the vector field. This form of Green's theorem paves the way for our generalization to the divergence theorem in the next video. Now let's move on and talk about Stokes' theorem. Before we present the statement of Stokes' theorem, I'd like to take a minute to talk about the motivation for this theorem and to try to explain how it relates to Green's theorem. Green's theorem gives us a relationship between the double integral over a region D in the plane and line integrals over the boundary of the region. However, since a lot of physics is three-dimensional, for applications to physics, we'd like to have a version of Green's theorem where the double integral is not over a region D that's contained in the plane, but over a surface S that's contained in R3. One of the ways to see how such a generalization is possible is to look at the second form of Green's theorem. When we derived this form of Green's theorem, we were thinking about the vector field f as being a two-dimensional vector field. However, the left-hand side of this equation makes sense even if f is a vector field in 3 dimensions. If we decide to think about f as a vector field in 3 dimensions, then we might also notice that the integrand on the right-hand side of the second form of Green's theorem is precisely the k component of the curl of f. This observation leads directly to the generalization of Green's theorem to surfaces, which is known as Stokes' theorem. What Stokes' theorem says is that for a vector field f in R3 and a surface S in R3, the oriented integral of the curl of f dot ds over the surface S is equal to the oriented integral of f dot dr over the boundary of S. Once again, in order to digest this formula, it's helpful to notice that it follows the same pattern that we saw in the fundamental theorem of calculus at the beginning of this video. The integral on the right-hand side is a two-dimensional integral. It's a surface integral of the second kind over the surface S. The integral on the left-hand side is a one-dimensional integral. It's a line integral of the third kind over the boundary of S. Here, orientation is important. We're assuming that S is an oriented surface, and we're assuming that the boundary of S is given the positive orientation with respect to the orientation on S. Finally, notice that the integrand on the right-hand side, the curl of f, is something which involves the derivatives of the integrand on the left-hand side. Once again, there are some assumptions that we need to make, but as long as the surface S and the vector field f are nice enough, the statement of Stokes' theorem is going to hold. As indicated by our discussion of applications to physics, Stokes' theorem has a physical interpretation. What it tells us is that the work done by a force F and moving an object around the boundary of S is equal to the flux of the curl of F across S. If you understand the statements in the sentence and you have a good physical intuition, then you can probably figure out why this should be true. What we're saying here is that under reasonable assumptions, it's actually a mathematically provable theorem. To conclude this video, I'd like to mention two nice applications of Stokes' theorem. First of all, Stokes' theorem gives us a simple proof that irrotational fields on simply connected domains are path independent. This is something that we talked about in the previous video. It's summarized near the top right-hand side of the vector calculus handout in the part that looks like this. What we're trying to say here is that Stokes' theorem gives an easy proof that if the curl of a vector field f in 3 dimensions is 0, then line integrals of the vector field are independent of path. Without trying to give a fully rigorous proof, it's relatively easy to see why this is true. Let's suppose that we have an irrotational vector field in R3, in other words a vector field that has curl 0. And let's suppose that we have two curves C1 and C2 connecting points A and B in R3. Think of the curves C1 and C2 as being the boundary of a surface in R3. And think about what happens when you compute the line integral of the third kind of f dot dr along C1 and then backwards along C2. By Stokes' theorem, that line integral should be the double integral over the surface of the curl of f. But by our assumption that the curl is 0, that double integral is 0. That shows that the line integral of f dot dr along C1 is equal to the line integral of f dot dr along C2. In other words, line integrals of the vector field are independent of path. Another application which I think a lot of you will like is that Stokes' theorem proves the equivalence of the differential and integral forms of 2 out of 4 of Maxwell's equations. The other 2 out of the 4 equations, by the way, are going to be covered by the divergence theorem in the next video. The two equations that we want to look at here are Faraday's law and Ampere's law. The differential forms of these equations, which you can derive from physical principles, are here on the left-hand side. I'm not going to have time to explain what all the vector fields and constants here are, so if you're not familiar with these equations, you might have to wait until you take electromagnetism. Anyway, what's important here is that in practice, often we use the integral forms of these equations. When I was a student learning electromagnetism, it always confused me why these were equivalent. In retrospect, I guess this is something which I should have seen as a corollary of Stokes' theorem. If you compute the double integrals of both sides of either one of these equations over a surface S, then on the left-hand sides you have something that you can apply Stokes' theorem to. Stokes' theorem tells you that the double integral over a surface of del cross E is the oriented integral over the boundary of the surface of E dot dr. Similarly, for the double integral over S of del cross B, it's the oriented integral of B dot dr. That explains very concisely almost all there is to see about the equivalence between the differential and integral forms of these equations. Well, that's the end of this video. In the next and final video of the series, we're going to talk about the divergence theorem.